Right, well, I'll get started. I think everybody's here is here. So, Heavenly Father, we thank you again for this opportunity we have just to meet and study your creation, and just pray that you be glorified in what we do, and we just have a good class today, Lord. In your name I pray, Lord Jesus. Amen. Let's see here. Lest I forget, here's the handy-dandy attendance sheet. So yesterday, we introduced the line integral, which is not always along a line. It's along a curve, generally speaking, but and I'll just recount our definition. The integral of f dot dr along a curve is equal to the integral, I'll use T1 to T2 today, T1 to T2 of f, and I'll use a different notation, R of t, dot dr dt, rather than that gamma I used yesterday, And of course, we can write that also as integral from T1 to T2 of, let's say, you could have, if we like, we could talk about PQR for the components of our three-dimensional vector. And of course, dr dt would be dx dt, dy dt, dz dt, right? dt. And if you take the dot product here, you have the integral from T1 to T2 of like P dx dt dt plus Q dy dt dt. Sorry, let me skip the dt out there. Plus R dz dt, all times dt, right? And as I explained last time, we also endorsed the use of the notation that this is equal to the integral over the curve of like p dx plus q dy plus r dz, all right? So mostly this top equation that I just wrote, I'm just saying these are notations that we use for the same thing, okay? So you can read it either way, all right? And we also give each one of these things a separate existence in the sense that the integral of, say, dx over a curve has a meaning, right? Like, for instance, if I say integral of p dx over the curve, what does that mean? Explicitly, that means the integral from T1 to T2 of p of r of t, all right, times dx dt integrated over dt, all right? Like, that's what I mean by integral of p dx over c, is that you choose a parameterization and you evaluate the function at the path and you multiply by the derivative in the x direction and you integrate over t. That's what the integral of p dx means. So symbolically, it's very, there's something really what's the word? Nice about it, natural about it, because you can kind of just think of the dt's canceling and leaving you a dx, right? But that's just a mnemonic. That's not actually what's happening, let's say. That's really just why our notation's a good notation, let's say. And all of this here concerns the curve, right, that goes from the initial point. So a typical point in the curve is like r of t. It's starting at r of t naught, and it's going to r of t1. Those are the terminal points of the curve, right? And r, technically speaking, is a mapping from t1, t2 to the curve, which at the moment I've written as a subset of r3, right? Now we can go to Rn. We can talk about the line integral in 4 or 5, however many dimensions. I don't usually do that, but there's nothing stopping us, all right? So any questions before I go on? We did a couple of these. We actually calculated a few of these yesterday, right? It's relatively straightforward, but it's kind of a pain. Why? Because it's what? well, yeah, it's a vector. The vector, see, vectors give me no pain. That's not what I'm talking about. There's a pain which you never get away from. That's the pain of integration. Like, integration is just a pain. Like, it takes, there's any number of simple formulas I can write down, and I say, go find the integral, and you'd be like, you can't do it, right? I mean, like, integration. There is a subset of functions which we can integrate, and that is a small set of functions in the world of all possible formulas, right? Just saying. So this theorem is really pretty awesome then. If f is equal to the gradient of little f on and near C, which going from, say, point P to point Q, all right, then the line integral of f dot dr over the curve is equal to, of course, the integral of the gradient of f dot dr over the curve, and it's straight up equal to f of q minus f of p. This theorem is important, obviously, and this has the name Fundamental Theorem of Calculus for Line Integrals, FTC for line integrals. All right. Now, unfortunately, we can't do this for all possible vector fields, all right? But for the vector fields which are equal to the gradient of a function, we have this theorem. Let's prove it. So here's a proof. Let's suppose that R goes from T1, T2 to C, where, you know, R of T1 is equal to P, and R of T2 is equal to Q, all right? And furthermore, I should clarify, what kind of path am I talking about here? This better be a smooth path, okay? I mean, that's a little bit too greedy. It really probably suffices for it to just be 1 times differentiable, but certainly the derivative of the parameterization needs to exist for what I'm about to do, okay? So then what's the definition? Well, we have integral over C of f dot dr is equal to the integral from T1 to T2 of what? For us, since f is, oh, and we're also assuming what? That f is equal to the gradient of little f, right? F is the gradient of a potential function. Now, I mentioned to you guys yesterday that makes this vector field what's called what? Conservative. So this is a conservative vector field we're talking about right now. So we've got the gradient of f, right, evaluated at the path, dot product with the velocity of the path, integrated over time. What is that? Can you recognize what we're looking at? What's this? We had the same calculus being central, for example, to the method of Lagrange multipliers, right? Remember this step? We composed, you know, a function with a path. We differentiated it, and then I went the other way. There I started with the derivative of the composition, and then I wrote this down because it's the chain rule. So, like the chain rule here is that integrand is really the total derivative of the composite of my potential function with my path. And just to be clear, the little f is the potential function, and such an f is called conservative vector field. Then what? Do you guys remember Calculus 1? What happens when we integrate a total derivative? Because that's what we have. Remember the net change theorem? It's the value of the function being differentiated at the upper bound minus the value of the function being differentiated at the lower bound. If you like, apply fundamental theorem of calculus part 2. And what we get then, of course, is f of r of t2 minus f of r of t1. That's right. This proof is about to come to a close. So this is actually f of q minus f of p, and we're done. All right. This is really, really nice, this theorem, when you can use it, because it means what? It means we don't have to parameterize the curve, right? All we have to do is find the potential function, and you can use that to calculate the work done by the force, if you like, or the circulation, if you prefer. Anyway, to calculate the line integral, let's do one. So example 1. Let's see here. Suppose we've got vector field f equal to, oh, I don't know, x y squared plus e to the x, comma, y sine y squared plus, let's see here, x squared y. And then finally, secant squared z plus 3. And suppose we want to calculate the work done, right? So here's the path I have in mind. We're going to start at the point 1, 0, 0, and we're going to end up here at the point, well, over here at the point 0. I guess this wasn't 1, 0, 0. This was probably 3, 0, 0. 0, 1, it looks like a 2, maybe. That's totally just made up, all right? And the path that we want to calculate the line integral along is as follows. There we go. That way. I don't know about you, but I personally do not want to parameterize that curve, right? Much less compose it with that vector field and try to calculate the integral directly from the definition, right? That would be horrible. But, oh man, I really hope this is a conservative vector field. So the question is this equal to the gradient of a potential function, right? Now, we could go through the rigmarole we went through before, where you could write down partial f partial x equals the first component, partial f partial y equals the second component, partial f partial z equals the third component. But let me tell you a secret. Once you know things, you guess. In other words, you just write down the answer, but you check it. So to get this, I need a 1/2 x squared y squared. Partial derivative with respect to x will give me that. Hooray. But I've also got an e to the x, so I better add an e to the x. All right. Now when I get to the partial f partial y, I automatically pick up that term from the purple, right? So I'll use some color coding. All of this from the purple terms. Let's see here. And then, all right, now I'm going to take care of y. I already took care of that piece. How about this piece? Well, that's a u substitution. I can add plus 1/2, well, excuse me, minus 1/2 cosine of y squared. Differentiate that thing. You get a minus sine of y squared times the derivative of y squared, which is 2y. The 2y cancels the 1/2, gives you y. Minus and minus gives you plus. You get back your y sine y squared term. Hooray. So we're done with that. And then I need another color. I guess I'll go back to red. Although this red is kind of dying. This one here, to get that, how do you integrate secant squared with respect to z? What do you got? Tangent. Tangent z. Derivative of tangent, secant squared. Hooray. 3. How do we get a 3? 3z. Right. And there you go. There's your potential function. You can check. And to be kind to the person who's reading this, you could say, you can check the gradient of f is equal to f. All right. Now, sometimes I actually do want to see you go through the iterative procedure of solving and then solving the next and so forth, but I do also think it's important for you to know how to just kind of write down the answer. Because it's not an unreasonable calculation to do, like I just did. In fact, it's relatively difficult for me to come up with examples where the method I just used doesn't work. Of course, if the vector field is not conservative and you try to do this, you'll get confused, right? That's the danger of this method, is that when the vector field's not conservative, right, and you try to do what I just did, you might talk yourself into something that's not quite right and convince yourself it's conservative when it's not. But I'm just talking about the hypothetical situation where you don't actually check your answer. If you actually check your answer, you should figure out, oh, I got to readjust my answer. And then if you try to readjust your answer and no amount of readjustment fixes it, well, then you know it's not conservative. Now, that's very open-ended, what I just said. And that's why the method I've showed you before, where you integrate one component, plug it into the next, integrate that, plug it into the next, integrate that, systematically using constants first of the two variables, then of one variable, and then of no variables, that like systematic substitution process is more reliable as an algorithm because it takes care of the case when it's not possible to do this naturally. You'll derive a contradiction. You can't derive a contradiction from guessing, right? At least I can't. Anyway, it is conservative, so let's do the integral. So we have the integral of f dot dr over this curve, which I forgot to give it a name. C. And that is f of, let's see, the endpoint is 0, 1, 2. The initial point was 3, 0, 0. I guess I should be a little bit concerned because I might have gone over, see, this is what's, I'm sorry guys, I have done a bad thing. I know it's hard to see from this perspective, but just to be clear, if I was to look at this jumbled mess, oh, rats, I just can't. This is illogical. I can't do this. Why is this illogical? I mean, you understand the idea of what I was about to do, right? Why can't I do it? Why can't I just take that evaluation and call it a day? What's the problem?
Here's the bill for the electric this month from October 1st estimated.
So x squared, y squared, that's good everywhere. E to the x, good everywhere. Cosine y squared, copacetic, it's okay. 3z, that's fine. Tangent z, it's got problems. Because the original vector field's got a secant squared z in it. That's 1 over cosine squared. Where is that not defined? Wherever cosine 0, which is what? On planes of odd integer multiples, odd integer half multiples of pi for z. So unless this curve fits between these horizontal planes of singularities for the vector field, right, it has to fit between plus or minus pi over 2 in order for me to do this calculation here. So my 2 is unfortunate. I can't put 2 there. That's too high because that's past pi over 2. So if you understand this whole mess is between the xy plane, let's say, and this point suitably modified, 2/3, there you go. Now we're good. Because now that curve, with the understanding that it's all between where the singularities are for the vector field, if we're there, then this formula is reasonable, and we can apply the fundamental theorem of calculus, and we're good. But you got to watch out for that. Domain matters. So anyway, here we got, oh, that's 0. E to the 0 minus 1/2 cosine 1 plus the tangent of 2/3. 2/3 times 3 is what? 2. And then I have to subtract, let's see here, that first term's still 0. And then I've got e to the 3 plus 1/2 cosine 9 minus the tangent of 0. Well, tangent of 0 is 0, and 3 times 0 is 0. So that's it. There you go. And of course, e to the 0 is 1. So we could simplify this as, 3 minus cosine of 1 over 2 plus the tangent of 2/3 plus the cosine of 9 over 2 and minus e to the power 3, I guess. I'm not going to, enough. If I've got an e to the 0 and a 2, I want to put them together just as a matter of, etiquette. Any questions? Yeah.
When you run into a discontinuity like that, do these things fall apart, or is there some infinite
Well, I've never really ran across, I can't remember having a vector field which had like a whole plane of singularities. So this is probably just like an artificial example that I just made up. But, well, sometimes you could have something where the domain makes, like, past a certain point out of bounds, right? Like, it could be that your vector field, for example, describes it could be like a gradient field of temperature in this room, right? Well, if we're using like x, y, z coordinates based on one of the corners in this room, z less than 0 is nonsense, right? Because it's outside of the room. So like that would be outside the domain. So we could have like artificial boundaries on the domain that you kind of run up against, that kind of thing. But yeah, we do have to worry about it. If you have a formula, then you have to face the music where the formula doesn't make sense. It would be better as kind of a point of order if examples were given with domains, but that's not our custom in calculus usually. We just give a formula, and then it's up to people to decide what's the maximal extent in which the formula makes sense, right? A lot of times there's just like one point that's out of order. For example, the one we had last time, if we look at f of xy, right, equal to, let's say, minus y over x squared plus y squared, x over x squared plus y squared, right? That one, what's the domain for that? Everything except the origin. That's right. So, and so yeah, the domain of f here is the punctured plane, right? And how about this? Is this a conservative vector field? Is this equal to like the gradient of some function? And when you say is the vector field conservative, by default, for example, if I say a function's invertible with respect to what? By default, if you say a function's invertible, it better be invertible with respect to its whole domain, right? Or if a function's increasing. If we say a function's increasing without qualification, we must be meaning it's increasing on its whole domain. Same for a vector field. If we say a vector field's conservative, we mean that you can find a potential function for which the gradient of the potential function is equal to the vector field on the whole domain. So when I ask the question, is this vector field conservative, I'm asking, can you find an f such that this holds on the whole of the domain, right? So can you tell me, guys? It's not. Why?
Because if you times partial left or partial squared half partial x partial y is different from partial y partial x.
Oh, actually, I think that they're equal.
There's a minus now.
Yeah, but there's an asymmetry. Huh. And I don't think that's the case. I think it works out. Now you've worried me. I didn't really want to do this. I'm going to regret this calculation. You're right that it's not conservative, but I don't think that is the reason. All right, so partial, I should check the y derivative of the x component, right? And that is minus 1 over x squared plus y squared. It's minus 1 over x squared plus y squared minus y times 2y over x squared plus y squared squared. All right? I'm doing product rule. You could do the quotient rule. We'll all agree at the end of this. This is minus x squared minus y squared. And I think I lost a minus somewhere in the story. That's supposed to be plus, right? Because I get a minus because it's reciprocal. Anyway, I'm pretty sure that's supposed to be plus. So plus 2y squared divided by x squared plus y squared squared, which is what? Y squared minus x squared, right? Agree? I hope we agree. But notice that the derivative with respect to x of the y component, it looks different in terms of the pattern. And that's a good thing. That's 1 over x squared plus y squared minus x times 2x over x squared plus y squared. Make a common denominator squared. Make a common denominator. We get x squared plus y squared minus 2x squared divided by x squared plus y squared squared, which is, lo and behold, y squared minus x squared over x squared plus y squared squared. Let me put this all, let me be three-dimensional here for just a second. If we extend to the third dimension, if we think about this vector field in a third-dimensional sense, what's the curl of the vector field? See, what you're doing here You were going back and checking the partial m partial y equals partial n partial x rule we had before. But what we're really looking at here is if we let's say g equal to, minus y over x squared plus y squared, comma x over x squared plus y squared, comma 0, right? Well, then the gradient, excuse me, not the gradient, the curl of g is 0, 0. And so there's no z dependence. The derivatives that appear in the curl in these two components are automatically 0 because of there's no z dependence and there's no z component. All right? There's no z dependence, there's no z component. So all of the first 4 terms in the curl that appear in the x and the y components of the curl are all 0. The only non-trivial component of this curl is the third one. But the 2 things that appear in the curl, the third one, are exactly the derivatives we calculated up here. You see? What you have here for the curl of g is partial x of gy, right? Minus partial y of gx, if you'll allow me that notation. But this right here is partial y of gx, and this right here is partial x of gy. And since they're equal, the curl is 0. That's not the reason this vector field is not conservative. Consider this. Yesterday, we showed that the integral of f dot dr, right, over the unit circle, right? Oh, actually, over a circle of radius r, we showed that this was equal to what? 2 pi, right? Remember? Okay? So what would we be able to argue if there was a potential function? If, check this out, if f is equal to the gradient of some other function, scalar function f, if it has a potential function, if it's conservative on the totality of that circle, you pick a point on the circle, let's say this point right here, r comma 0, right? That's a point. And what is that? That is both P and Q. It's the starting point and it's the ending point. It's the beginning and the end. And so, if you had that, what happens when you integrate around the circle? Well, you got yourself f of r comma 0 minus f of r comma 0, which is where I come from, that's 0.
2 pi is the same as 0.
Was is 2 pi is the same as 0? Oh, well, you got me there then. I guess I accept defeat. Although I might have to give up on mathematics if that's how it was. But it's not how it is it? It's not. Right? It's not. So then what? What can we discern from this? This is kind of disconcerting, right? Our handy-dandy is it conservative check didn't say no, right? It didn't say no. It said, maybe. But we did this integral yesterday, and we found 2 pi there, which says, no, it's not conservative. If you have the integral around a loop, a closed loop is non-zero, that vector field cannot be conservative because of this proof by contradiction right here, because of this reason. What's the rub? Why can't we find a potential function here? What is this thing? Can I explain it? What integrates to 2 pi when you go around a circle? No. You don't. What do we get? We get 2 pi. We go all the way around a circle. What would that be? Nobody? Degrees? It's the number of degrees? No, right? Number of radians. So what would be a logical thing to try here? How about maybe this is the differential of the angle? What's d theta? D theta is d of inverse tangent of y over x, right? Plus a constant. We'll call it epsilon. This epsilon is either 0 or plus or minus pi or pi, depending, or 2 pi, depending on what you want to make your convention for the angle in quadrants 2 and 4, where inverse tangent doesn't work. So this formula fails on the, it fails where? It fails on the y-axis, right? But it's good everywhere else. Let's make do with this. What happens when you calculate the total derivative of this? Well, you got partial x of inverse tangent of y over x, right? dx plus partial y of inverse tangent of y over x dy. And what is that? What is the derivative? How do you differentiate inverse tangent? It's 1 over 1 plus y squared over x squared, right? Times the derivative of y over x, which is, by the way, minus y over x squared here, plus, 1 over 1 plus y squared over x squared, times the derivative of the inside function y over x, which, with respect to y this time, which just gives us 1 over x dy. But look at that. That's exactly minus y dx plus x dy over x squared plus y squared, yo. So, yeah. So what we have then is that the integral, of minus y dx plus x dy over x squared plus y squared, right? It's actually the integral over d theta over the curve, right? And that's 2 pi. That's how to understand this example. But I still have to come back to my question, why is it not conservative? Besides the reason I already gave you, that if it was, we'd be able to, by the fundamental theorem of calculus for line integrals, prove the integral around the circle 0, and it is not. What's the rub? Why can't I just write? F is equal to, well, theta, really, right? Why can't I just say F is equal to theta? To be generous, that's what it is, right? I mean, we could use inverse tangent, right? We could say this. We could say f of xy is equal to the inverse tangent of y over x, right? That'll work. But where does it not work? It doesn't work where? It doesn't work at x equal to 0, right? But that's actually just an artificial shortcoming of the inverse tangent. See, we can meaningfully define angle all the way around a circle, but what has to happen? Like, there is something called, you could instead use this. You could use f of xy as what's called the argument, arg, of x plus iy. This is something we define in complex variables. The arg is going between minus pi and pi, for example. I forget which one's included, the pi or the minus. I think the minus pi. Well, no, the pi is included. There's another name for this in regular math, guys. I don't need to. I'm teaching complex right now. It's on my mind, but I think it's called like. God, if there's a formula that you can find in it's coded into, for example, like C++ or whatever. There's like a specific thing that will give you back angles from, from like 0 to 2 pi if you give it x and y, right? You are this computer on your physics test, right? I give you a vector, or in here, I give you a vector, I say find the standard angle. That's a meaningful function, right? I don't have a nice formula for it. Right? I don't have a nice formula for it, but it is a meaningful function. Where? I give you this here. I say that's theta, right? I'm over here. I say find that theta, theta 2, right? I'm down here. I say find that theta, right? You can find these angles, right? That define this, and when is it single valued? When is that a function? What do you need? You have to make a choice, right? Like we can insist, for example, that minus pi be less than theta be less than or equal to pi, right? We could choose angles like that, or you could choose from 0 to 2 pi. There's infinitely many different choices on how you're going to assign a set of angles, right? But for that to be a function, it has to be single valued, right? Which means you can't assign 2 angles to a given direction from the origin, right? What does that mean has to happen for any choice of angle assignment that you can possibly imagine? There has to be what? There has to be one angle, which is the dividing line, right? And what happens where that dividing line is? So for this choice, the bad spot is here. Right there on the one side of the line, on the upper side, you have pi. But on the lower side, you've got what? You've got angle pi up here. You've got angle minus pi down there. If you have a function that jumps from pi to minus pi in an infinitesimally small little region, is that a continuous function? It's not. That's a discontinuity of the angle. But what do we know about differentiable functions? Differentiable implies continuous. So what that means then is that your angle function is not differentiable here, which means you can't take the partial derivatives there, logically, which is why it fails to be a potential function. It's because of the discontinuity, which by necessity must come up at the angle jump. But at the same time, where could the angle jump be? That's up to you guys. It's a matter of convention. I put the angle jump here, but you could just as well have put the angle jump at pi over 2, or 30 degrees, or 22 degrees, or 42 degrees. Anywhere. It could be anywhere. And that's why you can choose a potential function for this vector field, just not on the whole domain. You can only choose it on like the whole domain modulo array. You have to lose array. And that's why this calculation had to work. You see, because it is conservative in some sense if we just limit our domain to not do what? To not encircle the origin. If we encircle the origin with our domain, whatever our choice of domain is, we're in trouble. As long as we don't do that, this calculation goes through. And so this example is actually really, really important. Understanding this example will put you on the right path for understanding the theory which follows. All right? So I had intended to get more covered today, but I think it's really good what happened. I think the questions that were asked and the discussion that's been had today, it's actually very valuable. So what we're going to do tomorrow is I'm going to define conservative vector field again, right? And I'm going to give you a list of 4 equivalent conditions, 4 equivalent characterizations of conservative vector field. The first is the definition, that it's equal to the gradient of a potential function. The second is that a conservative vector field has what's called path independence. If I integrate from one path, and if I integrate from another path, we get the same work done. A third characterization of a conservative vector field is that the integral around any loop, around any closed curve in the domain is 0. A fourth characterization of a conservative vector field is that the curl of the vector field is 0 and the domain of the vector field is simply connected. What does simply connected mean? Simply connected means that you can take a loop in your domain and you can smoothly deform it to a point without getting hung up on any point outside of the domain. The domain here is the punctured plane. And so there's a hole right here. So if I try to take this loop, for example, and I try to deform it to this point, I try to squeeze that loop down to the point. As I do that, I get stuck on the origin. This is not simply connected. And for that reason, this being 0, this derivative being 0, does not suffice to prove conservative. In fact, it's not. Now, we won't prove item 4. We'll prove part of what I just said tomorrow. The proof of the fourth thing requires what's called Green's theorem, which we'll get into before you know it. So anyway, thank you guys. Sorry I didn't get your quiz graded yet. I haven't lost it. I just forgot.